So moving out of the space of, how material science is driving innovation on the processing side of it, let's also talk about, the end of the life cycle, of a lot of these electronics. So, what roles does advancing material science and engineering play in reducing the harmful impacts of electronics waste, also known as e-waste for short?
So manufacturers, a few years ago, what they did was they realized that these electronic waste is a big nuisance. What do we do? They said, well, we'll give you an electronic that you can take some parts off and replace parts of. Your product will be as
Right.
good as new. So those replacement parts were out there, and we'll take those parts and recycle it the way they wanted it to do. Those things kind of didn't work much because they could not really keep up with the recycling process. And the manufacturing folks, they decided there is a need to design the new materials in general. We have to start with a material that is biodegradable. So there are a couple of things that I saw. There is a group in Stanford University, and they developed a fully biodegradable electronic circuit. And they made it with natural dyes that can dissolve in acid, and the pH is going to be very, very high. Dissolve in acid, but if it is a purely biodegradable circuit, that's the future. That's what we are looking at. That's one of the options. The other areas where some people were doing is they were pulverizing this e-waste into nanodust by cooling the various materials and then grinding them up into homogeneous material that are easy to reuse. There's a company, and it's based out of Canada, and they said, well, I'm going to use a technology that will use minimal amount of water and energy, and it will separate the metals and the non-metals from your electrons. And I'll use this with sonic vibration, and we use this recycled water and then separate these out. So there are ideas and some of the research that's being developed on it. So material science can help. One of the more recent ones, and I think it's not as electronic waste, but what people will appreciate is, about those packing peanuts?
Yeah.
Right? And they were all styrofoam based and polymer based for the longest time. Do you know, are they still like that?
I think those have moved to, so correct me if I'm wrong. It seems like you definitely know the answer to this, but the things that I've seen is, one, I've seen some packing peanuts now that are completely corn-based, which is interesting. And then
it's
I've
like
seen
cellulose-based. Yeah.
Right, so cellulose-based ones.
It will dissolve in water. You let it, if you have a large bag, you let it stay there for a longer time period, but it'll do the job. We want similar kinds of research that goes into making electronics. The problems are the heavy metals. We're talking about gallium here, and arsenides, and indium, and whatnot. So those heavy metals are the problem. So all the ones that I talked about, whether it is, separating metals from non-metals, sonic vibrations, or even magnetic fields to separate that out, those are what I feel are the future of controlling e-waste. Of course, all of this comes with consumers being a little more conscious about it and they doing their part.
Cool. So let's talk about that more. So in terms of the future, what would you say is the primary advancement in MSC that you see on the horizon that would drastically improve the electronics industry?
Material per se, there's not as much need of forming new materials or coming up with new material altogether. When we started this conversation, we were talking about the problems that we were having with the interface. It's about the connection between the two. You have a metal in one place, you have a ceramic in the other side. Your metal is sitting on top of a ceramic. You need them to talk and do what they need to do. Those are the problems. And I think the advancement will only come when we're able to focus and come up with solutions of those interfaces. So coming up alternatives for gallium arsenide, gallium nitride, or silicon, I don't see them driving any groundbreaking research. But yes, if you come up with processes that will help you make more reliable interconnections, it will help you make something that can withstand temperatures and voltages and other things. At the interface level, at the communication level, reliability level, those will be the advancements in what I believe. In terms of material, 2D materials are the in thing, is the buzzword. These are essentially monolayers, single layer slime materials.
They're only like nanometers thick, right?
Yes, so they're atomic scale. And then you layer them up, and graphene, for that example, it's more recent and it's happening. CNT was that.
Quick question, what is CNT?
Carbon nanotubes. Yeah, those are the ones that they were promising and they still are. But unless you have a compatible device interface, all critical advancements will not happen.
But which is also to say that though it may not be developing a new material per se, like you said. There's certainly a flavor of MSE that comes about with studying those interfaces between materials and really optimizing the type process control required to really get that to the place where you deem it necessary to make those leaps and bounds that we need.
That's correct. It's definitely material science, right? Surface phenomena that's happened. And it's just that we have to look deeper into these interfaces, try to come up with more engineering designs that can bypass or impede some of the challenges that we are facing these days.
That's incredible. It sounds like there's been a ton of really awesome electron microscopy done on some of these materials. So I should go Google around for those.
Yes, so characterization is big. Material science and electronics, they purposefully fail the electronics at different conditions. And then all they want to do is make cross sections after cross sections so they can throw it into SCM and TMs and all this beautiful in situ characterization that's happening these days. Put the current while the sample is in transmission electron microscope. It amazes me how much progress we have made in the last 25 years with all these beautiful technologies out there. And thanks to, material engineers all over the world. Of course, it's more interdisciplinary. It's not just physicists and engineers from other backgrounds that all come into play. But material science is what it drives me nuts even now.